Chemistry 101, Practice Exam 4, Part 2, Question 21. Which of the following is an example of a diprotic acid? And a diprotic acid is an acid that has two protons to donate. So let's take a look at the possible answers here. So HCl is a strong acid, but it's monoprotic. So we could write that down, monoprotic, and that means it only has one proton to donate, this one proton here, so this is impossible. The next one is NH2 minus. Well, NH2 minus is not an acid, so we're just going to scratch this one right off. The next one is H2SO4. That's sulfuric acid, and it is a diprotic acid because what? It has two protons, two acidic protons. Therefore, this is going to be the correct answer. So the correct answer is C. You take a look at D, that's methane. CH4 is methane. That is not an acid. And NH2 minus, that's the conjugate base of ammonia. And therefore, that is not an acid, and it's definitely not a diprotic acid. Question 22. Which statement concerning the relative strengths of acids is false? First answer says strong acids produce strong conjugate bases and weak acids produce weak conjugate bases. Well, that's the correct answer right away. That is a false statement because strong acids produce weak conjugate bases and weak acids produce strong conjugate bases. And that's something that we looked at in chapter 8, is how a strong acid, when it loses a proton, it produces a weak conjugate base, and how a weak acid, when it loses a proton, it produces a strong conjugate base. If we take a look at the other possibilities, let's just take a look. It says a strong acid completely transfers its protons to water, and a weak acid only partially transfers its protons to water. That is correct because strong acids are strong electrolytes and they completely dissociate, whereas weak acids are weak electrolytes and they only partially dissociate. C, strong and weak acids differ in their extent of proton transfer to water. That is also a true statement. Strong acids will donate or dissociate more of their acidic protons to water than a weak acid will. D, strong acids are good proton donors, weak acids are poor proton donors. That's true. And then the last one, a strong acid produces more hydronium ions in water than a weak acid, of course. There we go. So the answer for 22 is A. Question 23, what is the pH of a 0.035 molar hydrochloric acid solution? You need to know the formula that pH is equal to the negative log of the concentration of H+, or we can write it as hydronium. And we know that since hydrochloric acid is a strong acid, so since HCl is a strong acid, it's one of the strong acids that you have to memorize. When we put that in water, it's going to completely dissociate 100% to produce hydronium, and it's also going to produce the conjugate base of HCl, which is chloride. And that means that if I have 1 mole, if I start with 1 mole of HCl, it's going to dissociate to produce 1 mole of hydronium according to my balanced equation. So that means if I start it with 0.035 molar, or moles, we'll just assume we have 1 liter. If I start it with this many moles of HCl, I'm going to have this many 0.035 moles of my hydronium. And we can assume a 1 liter solution, so that means that the concentration of our hydronium is also going to be 0.035 molar. And so we can plug that number into our formula, so it's going to be the minus log of 0.035, and I end up with my pH being equal to 1.46, and that's B. Now remember, since we have two significant figures in our concentration, we're going to report our pH to 2 digits past the decimal place. Question 24 says a patient's urine sample gave a reading of 8.2. I think that means gave a pH reading of 8.2. What is the value for the concentration of hydronium in this solution? We just looked at this formula that pH is equal to minus log times the concentration of hydronium, but we want to solve for the concentration of hydronium. And when we rearrange that formula, we get that the concentration of hydronium is equal to 10 to the negative pH. And therefore, we can just plug our pH into this formula, 10 to the minus 8.2. And we get that our concentration of hydronium is equal to 6 times 10 to the minus 9 molar. And is that one of the answers? Yes, it's this one here. They put 6.0. In order for it to be 6.0, this would actually have to read 8.20 in order to follow the correct rules for significant figures. But we'll just say that it's close enough. Question number 25. What is the pH of a 1.0 times 10 to the minus 4 molar solution of potassium hydroxide? Well, potassium hydroxide is a strong base. In strong bases, it is a strong base. It is going to completely dissociate to give you potassium ions and hydroxide ions. That means that all of the potassium hydroxide, so this 1.0 times 10 to the minus 4 molar, that's going to completely dissociate into K plus and hydroxide. That means that the concentration of my hydroxide is going to be equal to 1.0 times 10 to the minus 4 molar. Now, if I want to figure out the pH, I know that the formula for pH is that pH is equal to minus log times the concentration of hydronium. So the question becomes, how do I get the concentration of hydronium? And in order to get that, you need to know that the Kw for the auto ionization of water is equal to the concentration of hydronium times the concentration of hydroxide. You also have to know the value of Kw, which is 1 times 10 to the minus 14. So let's rearrange that and solve for concentration of hydronium, and we get that the concentration of hydronium is equal to Kw divided by the concentration of hydroxide. Now we can plug our numbers in. 1 times 10 to the minus 14 divided by 1.0 times 10 to the minus 4, and you can probably solve that in your head, and that's going to be equal to 1.0 times 10 to the minus 10 molar will be our concentration of hydronium. Now this number, the Kw, you can assume that this has an infinite number of significant figures, and that's why I can report the concentration of my hydronium to 2 significant figures. Now I'm going to change colors again, and we'll put pH is equal to minus log times the concentration of our hydronium, and therefore the pH is going to be equal to minus log times the concentration of 1.0 times 10 to the negative 10, and we get that our pH is equal to 10.00, and that is A. Number 26, a sample of black coffee was measured to have a concentration of hydronium equal to, our concentration of hydronium is equal to 7.94 times 10 to the minus 6. We'll assume that's moles per liter. What is true about this solution? The first answer says, or first possible answer says, the pH of the solution is 7.94. Let's do the math here. pH is equal to minus log times the concentration of hydronium. And therefore, we can plug in our concentration. pH is equal to minus log of 7.94 times 10 to the negative 6. And we get that our pH is equal to 5.100. Therefore, that is not 7.94. The next one says the solution is acidic. Well, if I have a pH of 5.100, you know that any pH below a pH of 7, which is neutral pH, is acidic. Therefore, this is acidic. Therefore, this is the true statement. The solution is acidic. If we take a look at C, it says the solution does not contain any hydroxide ions. Well, that's not true. We could solve for the concentration of hydroxide using the formula Kw is equal to concentration of hydronium multiplied by the concentration of hydroxide. The next one says the solution contains less hydronium ions than pure water itself. In pure water, we know from Kw being equal to the concentration of hydronium times the concentration of hydroxide, we can solve, and we know that the concentration of hydronium in pure water is actually 1 times 10 to the minus 7 molar. And this number, 7.94 times 10 to the minus 6, is greater than this number. Therefore, this is not true. And then the last one is not true as well. So the answer is B. The solution is acidic. Question 27. If the hydronium ion concentration of an aqueous solution at 25 degrees Celsius is 5 times 10 to the minus 6 molar, what is the hydroxide ion concentration? Well, we know our formula Kw is equal to the concentration of hydronium multiplied by the concentration of hydroxide. We can solve that for the concentration of hydroxide. We just have to do some simple algebra, and the concentration of hydroxide is going to be equal to the Kw divided by the concentration of our hydronium. We can plug in some numbers. 1 times 10 to the minus 14, that's our Kw value. You need to have that memorized. And we're going to divide that by the hydronium ion concentration, which is 5 times 10 to the minus 6. And we get that the concentration of our hydroxide is equal to 2 times 10 to the negative 9 molar. 2 times 10 to the negative 9. There we go. B. Number 28, titration of 15 milliliters of a sodium hydroxide solution required 7.4 mils of a 0.25 potassium nitrate solution. This is a typo. So this is not potassium nitrate. It should say HNO3. So it should read nitric acid. So it's a titration of sodium hydroxide using the standard solution, and the standard solution is a 0.25 molar nitric acid solution, and it's asking us to determine what the molarity of the sodium hydroxide is. The first thing we should do is write out the neutralization reaction that occurs when we neutralize sodium hydroxide with nitric acid. So sodium hydroxide plus nitric acid. I'm going to leave out the states of matter, which are all aqueous. And when I react an acid and a base in a neutralization reaction, I end up with a salt plus water. And in this case, the base and the acid are going to react in a 1-to-1 ratio to produce water and sodium nitrate. And therefore, you can see that the stoichiometric ratio between sodium hydroxide and nitric acid is 1-to-1. And since we're doing a titration, when we get to the equivalence point, we will know that the number of moles of sodium hydroxide will be equal to the number of moles of nitric acid. Therefore, in order to calculate the concentration of sodium hydroxide, we need the number of moles of sodium hydroxide divided by the volume of sodium hydroxide. Now, we already have the volume of sodium hydroxide. It's given to us. It's 15 milliliters. I'm just going to convert that into liters in my head. So that would be 0.015 liters. And therefore, what we're really solving for in this problem is the number of moles of sodium hydroxide. We need to have that number to put in the numerator. So how are we going to do that? Well, we're given the number of milliliters, or the volume, of nitric acid, and we're given the molarity of nitric acid. So let's use some dimensional analysis and solve for the number of moles of nitric acid, and then use our balanced equation to determine the number of moles of sodium hydroxide. Again, I'm going to go ahead and convert this volume into liters in my head. So 7.4 divided by 1,000. So I'm going to do the math up here. 0.0074 liters of my nitric acid. And the molarity of my nitric acid is 0.25 moles of HNO3 for every 1 liter of HNO3. So you can see that liters of HNO3 are going to cancel out. Then, in order to determine the number of moles of sodium hydroxide, I'm going to look at the stoichiometry in my balanced equation. And I know that for every 1 mole of nitric acid, I consume 1 mole of sodium hydroxide. And these units are going to cancel out as well, and I'm going to end up with the number of moles of sodium hydroxide. And the number of moles of sodium hydroxide, I've done the math already, is 0.00185 moles of sodium hydroxide. And therefore, I'm going to plug that into my numerator in this expression down here. 0.00185 moles of sodium hydroxide divided by the volume 0.015, oops, I'm missing a sig fig there, 0 liters. I plug that into my calculator and I end up with, what do I end up with? I end up with 0.12 molar. There we go, 0.12 molar. There should only be 2 sig figs in the final answer because there's only 2 sig figs in this volume and there's only 2 sig figs in this concentration. So technically I could have reported that to 2 sig figs, but when you round the answer, you get 0.12 molar, which is E. 29. Butyric acid is a weak acid. Which reaction equation properly represents the dissociation of butyric acid and water? Anyhow, so butyric acid is a weak acid. Which reaction equation properly represents the dissociation of butyric acid? And we know that if we have a weak acids only partially dissociate. Therefore, we cannot use a one-direction arrow. We have to use the equilibrium arrows, right? This represents partial dissociation. Therefore, we can scratch this answer out right away. A, we can get rid of D, we can get rid of E because they all have unidirectional arrows. Now, if I look at B and C, in B, I have my butyric acid molecule. In an organic acid, the acidic proton is the one that always comes at the end of the COOH. So this one here, the R, that just represents a generic organic group. Anyhow, but this proton here that I circled in blue, that's the acidic proton. Now, the weak acid is going to donate the proton to water to produce hydronium, but then I should get a conjugate base. And you can see the problem here is that I haven't lost the proton. Therefore, the correct answer must be C. And you can see in C that the acidic proton is lost to form the conjugate base of butyric acid. And of course, I form the conjugate acid of water, which is hydronium. Therefore, the answer is C. Number 30. Sodium hydroxide can react with phosphoric acid in a neutralization reaction. What is the reacting ratio of sodium hydroxide to phosphoric acid? Well, phosphoric acid, H3PO4, this is a triprotic acid. Phosphoric acid isn't a strong acid, but it's got 3 protons, right? H, and then you see the subscript 3. That means it's got 3 protons to donate. And in sodium hydroxide, I only have 1 hydroxide in sodium hydroxide. And for every acidic proton, it's going to take 1 hydroxide to neutralize that and form water. Because when we react an acid and a base, we get a salt plus water. That means when I take my phosphoric acid, so H3PO4, I'm going to have to react it with 3 moles of sodium hydroxide in order to produce 3 moles of water plus sodium phosphate. And therefore, the ratio of acid to base is 1 to 3. Now, they're asking you for the reacting ratio of sodium hydroxide to phosphoric acid. You can see there's 1 to 3 and 3 to 1, so you have to read the question carefully. And base to acid, sodium hydroxide to phosphoric acid is 3 to 1. Therefore, the answer is E. Question 31. Which one of the following correctly represents a conjugate acid-base pair? A conjugate acid-base pair, let's take a look. The first one is hydronium and hydroxide. Hydronium is an acid and hydroxide is a base, but they are not a conjugate acid-base pair because in a conjugate acid-base pair, if I take an acid like HA and I react that with, or I put that in water and let's say it's a weak acid, it's going to partially dissociate to give me A- plus hydronium. Therefore, the acid and conjugate base are this, right? The conjugate base is what is left over from the acid after it's donated a proton. If hydronium donates a proton, you form water, not hydroxide, right? Because you would only lose 1 proton, and then you would get H2O instead of H3O+. So this is impossible. The next one for the same reason. If water donated 1 proton, right, if it behaved as an acid and donated 1 proton, I would get hydroxide, not O-, which isn't even a thing. The next one is the correct answer. H2CO3, that's carbonic acid, and if carbonic acid loses 1 proton, it becomes HCO3 minus, or the bicarbonate ion. Therefore, this is my conjugate acid-base pair. You take a look at the next one, HCl and Cl2. Well, that's not even anywhere close. That's hydrochloric acid and chlorine. And the next one, the problem with E is that if carbonic acid, it would have to lose 2 protons in order to form carbonate. And that doesn't fit the criteria for being a conjugate acid-base pair like I described in this red box here. Question number 32. Which of the following correctly describes what is meant by the term neutralization? You should have the term neutralization memorized, and a neutralization is when you react an acid and a base to produce a salt and water. That's a definition that all chemistry students should be aware of, and that is described by E, the reaction between an acid and a base to form a salt and water. Number 33, what is the conjugate acid of NH2-? And we looked at, if we have a weak acid and we put that in water and it dissociates to give us a conjugate base, or the conjugate base of the acid plus hydronium, we could do the same thing here. If we assume that this is our base, what would be the conjugate acid? Well, if this is a conjugate base, what is a conjugate acid? The conjugate acid is what happens when it gains, or it takes on H+. So if NH2-, if you add H+ to it, the positive and minus charges cancel out, and you end up with what? You end up with NH3, or ammonia. And therefore, ammonia would be the conjugate acid of NH2-. It's a polyatomic ion that we don't look at in this class, or we don't have to learn the name of, but it's called amide. Question 34, what is true about a solution whose pH is less than 7? And by now you should be aware that when you have a pH equal to 7, this is what we call neutral pH. And if you have a pH of less than 7, pHs below 7 are acidic. Therefore, if we're looking for a true statement, A is definitely not true because it is an acidic solution, not a basic solution. The next one says it has a hydronium ion concentration less than 1 times 10 to the minus 7. 1 times 10 to the minus 7 molar would be the concentration of hydronium at a neutral pH, at a pH of 7, because if you take pH is equal to minus log of 1 times 10 to the minus 7, you get a pH of 7. And since the pH is less than 7, the hydronium ion concentration would have to be more. Therefore, this is not a true statement. The next one, the hydronium ion concentration, it has a hydronium ion concentration that is higher than pure water itself. Yes, absolutely. This would be the correct answer, because in an acidic solution, you're going to have more hydronium ions than you would at a neutral pH. Question 35 says, HCl is a strong electrolyte. What do we know about strong electrolytes? Is that they undergo complete dissociation. There we go. A bottle of HCl contains a label that is 0.015 molar HCl. Which statement concerning this HCl is false? It says here, the solution has a higher concentration of hydronium ions than hydroxide ions. This is a true statement because at neutral pH, the concentration of hydronium and the concentration of hydroxide will be equal to each other, but since we have an acidic solution, we're going to have more hydronium than hydroxide, so this is a true statement. The next one says the solution contains dissolved hydronium and chloride ions only. No HCl molecules are present. This is also true because we know that a strong electrolyte is going to completely dissociate. So if I take my HCl and I put it in water, it's going to completely dissociate to give me hydronium plus chloride. Therefore, B is a true statement. The next one says the pH of the solution is 1.5. Well, I can assume that since HCl completely dissociates, right, it undergoes complete dissociation, if I have a bottle that's labeled 0.15 molar HCl, that means I'm going to have an actual concentration of hydronium, which is 0.015 molar. Therefore, I could plug this into the formula. pH is equal to minus log times the concentration of hydronium. And I can put in minus log times 0.015. And when I do that, I get a pH equal to 1.82. Therefore, this statement is false. Question 36. What is always a characteristic of a solution that contains a buffer? In A, it says a solution resists large changes, or the solution resists large changes in pH when small amounts of acids or bases are added. That is the definition of what a buffer is. So this is characteristic of a buffer solution. And remember, when you add small amounts of acids or bases to a buffer solution, it doesn't mean that it resists all changes in pH. And that's what it's saying here. It says in B, the solution maintains constant pH. That is not true. The pH will change, but the point is that it only changes slightly, so it resists large changes. And therefore, the answer is A. If you look at C, the solution has been diluted by the addition of solvent. It's not the correct answer. The solution contains a small amount of solute dissolved in a large volume of solvent. Well, a buffer can have many different concentrations. And then E, the solution is neutral and has a pH of 7. Buffer solutions can have a wide range of pHs depending on what your weak acid and conjugate base or your weak base and conjugate acid are. Question 37. Which of the following statements concerning a voltaic cell is false? The first statement says the oxidation half reaction occurs at the cathode. I find it easy to remember that oxidation occurs at the anode and reduction occurs at the cathode. And the way that I remember that is that oxidation and anode both start with a vowel. Right? They both start with vowels, and reduction and cathode both start with consonants. Therefore, A is the correct answer. It is a false statement. If you look at B, the anode and cathode are separated by a salt bridge. That is a true statement. The cell consists of 2 half cells. That is true as well. D, the anode, at the anode of a substance, a substance will lose electrons. That is correct because the anode is where oxidation is occurring, and you remember oxidation is losing electrons. Therefore, this is a true statement. And a voltaic cell uses a redox reaction to produce electrical energy. This is also true. Question 38 says classify the following reaction as either decomposition, redox, combustion, acid-base, or precipitation. We can see it's not a decomposition reaction. There's nothing decomposing here. It's not a combustion reaction because a combustion reaction is where we take a compound, combine it with oxygen, and we get water and carbon dioxide as products. Acid-base, neither of these are acids or bases, and a precipitation reaction, you'd have to form a solid in order to do that, and everything is aqueous. Therefore, the answer must be redox, and if we take a look at what's really happening here, you can see you're going from cerium 4 plus to cerium 3 plus. That means it is gaining electrons, and you remember from oil rig that oxidation is losing and reduction is gaining electrons. Therefore, the cerium is undergoing reduction, and you can't have reduction without oxidation. And the iron 2 plus is losing an electron to become oxidized to iron 3 plus. Therefore, this is an oxidation reduction reaction, or as I like to call it, a redox reaction. Question 39. Choose the best classification of the reaction represented by the following equation. Well, like I just told you, when you take a compound and you combine it with oxygen and you produce carbon dioxide and water as products, this is a combustion reaction. And this is actually showing the combustion of the molecule glucose. And question number 40, which statement correctly describes what's happening in the reaction below? I'm going to rewrite the reaction. So we have 2 magnesium plus S2 is giving us magnesium sulfide. This equation is not balanced, so I'm going to balance it for us. Anyhow, there we go. Magnesium sulfide. Anyhow, let's fix the stoichiometry here. Now our equation is perfectly balanced. If we look at the oxidation states of magnesium and the sulfur, well, these are both pure elements as reactants, so their oxidation states are both 0. But metals like magnesium like to lose electrons. Magnesium has 2 valence electrons, and it's becoming magnesium plus 2 is going to be the oxidation state, and my sulfur is undergoing reduction to produce sulfur with a -2 charge. So this shows all the oxidation states, and if we examine what's happening here, the magnesium is being oxidized because it's losing electrons, and we know that oxidation is losing and reduction is gaining, and my sulfur is going from 0 to -2, therefore it's gaining electrons, which of course have a negative charge. And if we take a look at the possible answers, it says magnesium is the oxidizing agent. That is untrue. Magnesium is being oxidized, therefore it is the reducing agent. This is incorrect. The next one says magnesium sulfide is the reducing agent. Well, magnesium sulfide is a product, so this is not the correct answer. As well as C, it says magnesium sulfide gains electrons. Magnesium sulfide is the product, not a reactant. D, magnesium is oxidized. We already agreed on that magnesium is undergoing oxidation. And the sulfur, the S2, is losing electrons. That is not true. It is actually gaining electrons because it is being reduced.